So far, we spent the whole course discussing linear functions. The next type of function that we want to add to our repertoire is the exponential function. Let's look at this example in a few ways. Suppose we begin with a population of 10 strep bacteria, and the size of the population doubles every hour. Numerically, the situation looks like this. At the beginning, we have a population of 10. Then 1 hour later, we have a population of 20. 2 hours later, we double the population again so that it's now 40. Notice that as we increment time by 1 hour, the population is multiplied by 2. We'll talk more about this later, but the fact that we're multiplying at each step rather than adding is a hint that an exponential model is much better than a linear model. If we plot those points of data and connect them by a smooth curve, we see again that a linear model is not appropriate. There's relatively little change between hour 0 and hour 1, but there's pretty significant change between hour 3 and hour 4. A linear function would demand that we have constant rate of change throughout, and its graph would be a line. But we see we have a different rate of change at different times, and so we have to connect it by a curve that's increasing more rapidly later in time than it is earlier in time. How can we develop an equation that captures this information? Whenever we increment time by 1 hour, we multiply the population by 2. So we could write the population column in a strange way. We could begin with the population of 10 at time 0, and then at time 1, what we have is 10 times 2, because we've incremented time once, and each time we do so, we're supposed to multiply the population by 2. So at hour 2, we have the 10 that we began with, times 2 for the first hour, and times 2 for the second hour. And at time 3, so 3 hours later, we have the 10 population that we began with, times 2 for the first hour, times 2 for the second hour, and times 2 for the third hour. A more concise way to write down that repeated multiplication is to use exponents. So at time 0, we've multiplied by 2 no times, so that's 2 to the 0. At time 1, we've multiplied the initial 10 by 2 only 1 time, so that's 2 to the first power. At time 2, we take the initial 10 population that we started with, and we multiply by 2 a total of 2 times, so that's 2 squared, and so on for the other columns. Writing it in this way suggests an equation that the population of the colony after t hours is the initial 10 that we began with, multiplied by 2, and then the number of times you should multiply by 2 is the value of t. So we have an equation that population is equal to 10 times 2 to the t power. So what kind of data is an exponential function used for? From a numerical perspective, we might say that exponential functions model repeated multiplication of a single value. In this example, each step forward in time corresponded to a multiplication of the population by 2. Or from an algebraic perspective, we might say that it's a function that can be modeled by c times a to the x. Here, c is the initial value, so it's the output of the function at time 0. For us, this was the 10 population that we began with before we watched the population grow. The value of a is that constant multiplier, and this is called the growth factor. For us, it was that 2 that we multiply each time we step forward. Saying that a value grows by a certain percent is actually an exponential function as well. So suppose we have 50 rabbits to begin with, and their population grows by 60% each year. Before we try to make an equation, let's think about how we would figure out the population for next year. We have 50 rabbits currently, and we expect the population to increase by 60% of the current population. So that's 50 plus 0.6 times 50. That's the original 50 plus the 60% growth. If I factor out the common 50, then I have 50 times 1 plus 0.6. So that's the same as saying 50 times 1.6. So to represent the 60% growth, I can multiply the current population by 1.6. The advantage of expressing the growth in this way is that it fits nicely into the exponential model that we have. Initially, I begin with a population of 50. And the next year, how do I determine the population? I say it's the current population, which is 50, times 1.6. And then what about the second year? I have the 50 rabbits that I began with. And then in the first year, I multiplied by 1.6 to get a 60% growth. And then in the second year, I multiplied by 1.6 to get another 60% growth. So that's 50 times 1.6 times 1.6. Just as we did before, we might use exponents instead of the repeated multiplication. Now I can see an equation that models this growth. I have the 50 rabbits I began with, and then times 1.6 to the power t, where t is the number of years that I'm interested in. In a problem with percentages, the percentage is usually called the growth rate, as opposed to the growth factor that's used in the exponential model. And the relationship between those two is what we just witnessed, that the growth factor is equal to 1 plus the growth rate. So for our example, we said the growth factor was 1.6, and we got that from 1 plus the growth rate of 0.6.